everyone, welcome to GEMCHEM. Now today's video is on alkenes part 10 video, and here we will deal with hydroboronation of alkenes. Now before starting, if you have not watched the previous videos on alkenes, you can watch it. I will give the link in the description box as well as the I button present above this video. Now let us start today's video. Now what do we mean by hydroboronation? It is basically an addition of a hydrogen and boron across a double bond. Now when an alkene is treated with boron dissolved in THF, it undergoes hydroboronation to yield a trialkyl boron usually. Now see, if diboron when dissolved in THF, it forms a acid-base adduct. Okay. Now the reaction is like this, that is, if this is the alkene, then the boron gets attached to the terminal part. That is, this terminal carbon is being attached by a boron and this part is being attached by a hydrogen. Now boron has a valency of 3, so there is 3 alkene molecules attached to it. Now hydroboronation involves addition of BH3 to the carbon-carbon double bond, because from this adduct we get only the BH3 moiety. Okay, so with the hydrogen attaching to one of the doubly bonded carbon and boron to the other, and we usually see that the boron gets attached to the one carbon which is less hindered. Okay, now when a terminal alkene is used, boron is attached with the terminal carbon. Now this structure is basically represented by this, that is boron attached with 3 alkene. Now let us see the mechanism. The mechanism basically followed is a concerted mechanism, but we will see it in details. Now see, we have seen that this is the alkene which is being taken and the diboron actually produces BH3 moiety. Right. Now see this one. The most important thing is this is electron rich, whereas boron is electron deficient. So first what happens is this one, that is the alkene, tries to donate the pi electrons, and during donation it forms a pi complex, that is this one is the pi complex. We can write this as pi complex. Now see, there is 2 positions for boron to get attached, right, here or here. Now if we draw the first possibility, that is if we take this way, then our transition state will look like this, CH2, and here there will be boron and here there will be a hydrogen. This is the hydrogen and here is the hydrogen. Now first of all, since this pi donation has taken place in the boron, so boron becomes delta negative and this carbon becomes delta positive. Now we will show the dotted bonds because these are forming or breaking. So we have shown it. Here is a R present. So this is the transition state formed when we are going to attack boron from this side. Now we will see when boron attacks from the another side, that is this side. Right. Now what is the transition state? We write same way, CHR, and here one bond CH2. Here we have a hydrogen and here we have BH2 unit. So now what happens? This becomes dotted and we can see that this boron center is delta negative and this is delta positive. Now we generally observe this transition state and not this. Why? Because in both cases we see that 4-membered cyclic transition state is observed, but a secondary carbocation is more stable than a primary one. Okay, and the boron attach itself to a less hindered carbon and we see that this carbon is less hindered with respect to this one. Right, the steric hindrance is less in between the alkyl groups. Number of hyperconjugative hydrogen is higher also in this case. So we take this as our main transition state. So this path is not followed at all. This transition is not formed. Now next step, we will see what happens. In the next step, this is formed. R, CH2, CH2, B, H and H. Now this again undergoes a reaction with another alkene and this hydrogen is taken. Then another proceeds with another alkene and this hydrogen is being taken. Then what we get ultimately is this one. Here 3, B and this is R. Right. This is the mechanism and this occurs in concerted process, that is takes place through a 4-membered cyclic transition state formed by addition of a polarized BH bond to the alkene double bond. Okay. Now we will see, as 4-membered cyclic transition state is involved, addition occurs in syn manner in the same side. That is, we are seeing that addition is taking place from the syn, that is same side. It is regioselective and stereoselective. That is, boronation taking place preferentially on the least hindered side of the alkene. Now at time of hydroboronation, alkene can act as nucleophile as well as electrophile. So now see, in the first step we see that the pi orbital attacks this boron. So what it is doing, this pi orbital of the alkene donates electron to the vacant p orbital of boron, and this is HOMO and this is LUMO. Whereas in the second case, the s orbital of hydrogen donates the electron to this carbocation, that is the LUMO of alkene, which is a pi star. So this is the interaction taking place, which is nucleophilic attack plus the electrophilic attack. So we see that here in the first step, this one is acting as a nucleophile, whereas this alkene in the second step is acting as electrophile and accepting electron from the hydrogen s orbital. Now this HOMO-LUMO concept is being explained with MO diagrams in the organic chemistry video. You can watch it. I will give the link in the description box as well as the I button present above this video. Now let us see the next part. Now see this one. First of all, hydroboronation of mono and disubstituted alkenes with borane gives rise to trialkyl borane product. But when we come to trisubstituted and tetrasubstituted alkenes, then there occurs formation of dialkyl borane and monoalkyl borane. So we see that 2-methyl-but-2-N on reaction with B2H6 produces decimal borane containing 2 alkene units and BH. Whereas in this case 2,3-dimethyl-but-2-N we see on reaction forms hexyl borane, which contains only 1 alkene unit and BH2. Now we see this is a 1Z5Z cycloocta 1,5-diene. On reaction with B2H6, it generally forms the 9-BBN molecule, that is this one, formation of a bridged boron. Okay, now we will see what happens with respect to hydrogenation when many functional groups are present and when addition takes place in unsymmetrical alkene. Now if we look carefully, we see that there is dominance of the terminal alkene carbon to be boronated, that is 94%. Similarly in this case 98%, where there is less steric crowding. But in this case, if we observe, here preference is increasing for this part when OET is being present. Similarly here, when Cl is being present, 60%, 40%. So the percentage is increasing for this carbon, that is non-terminal carbon. And the last one in this case, if we see here, see that here the ratio is somewhat nearly equal, right? But here in this case we see that this part has more steric bulk than this one. So why is it so? In absence of strongly polar neighboring substituent, the reaction is highly selective. These two cases are for absence of strongly polar neighboring substituents. The selectivity decreases with the increasing electronegativity of substituent. So if its electronegativity present in the substituent increases, then the selectivity decreases. 1,2 disubstituted alkenes has less difference in percentage. That is, when there is 2 substitutions in the 2 carbons, then their selectivity decreases. It is difficult to get selectivity for a particular double bond when other double bonds are present. Suppose there are 2 to 3 double bonds present in a molecule, then if we require one double bond to be boronated, then selectivity is very difficultly observed. Now these difficulties are overcome by hydroboronation using substituted boranes. Now we have already seen the formation of decimal boron, texyl boron and 9-BBN. These are more selective and less reactive than diboron. So they are easily used to form the required product. Now if we see this alkene, we see that it is disubstituted, and we have already seen the problem with the disubstitution. When 1,2 is disubstituted, it has very less difference in percentage. So we use C5H11 whole 2 BH, that is decimal boron, and we see that the ratio has improved. Here the case where there is less hindrance, the ratio is 97:3%, right? Here hydroboronation has taken place. Now if we see for the terminal alkenes and the internal alkenes, we see that for hydroboronation, terminal alkenes react more rapidly than internal alkenes, and the Z alkenes reacts more rapidly than E alkenes. Now if you don't know the concept of Z alkenes and E alkenes, you can watch the IUPAC nomenclature series. I will give the link in the description box as well as the I button present above this video. Now see, the non-conjugated dienes which are away from the conjugation is more rapidly hydroboronated than the conjugated one. So what do we mean by conjugated and non-conjugated diene? Suppose if we see, this is a moiety, right? And we see here is a double bond and here is a double bond, whereas here is a double bond. So just see that this double bonds are conjugated. But in this case, no scope of delocalization has been observed. This is not possible. So this hydroboronation will prefer to be done in this carbon. Okay. Now if we see for the reaction of this one, we have seen that terminal alkenes react more rapidly with the internal alkenes. So we see that this is internal alkene and this is terminal alkene. So on adding 9-BBN, we see that reaction takes place on terminal alkene. Now hydroboronation of dienes with boron itself lead to polymer formation. Now if we try to do the hydroboronation of dienes with only boron, then there is a polymer formation, and texyl boron promotes its hydroboronation to form cyclic or bicyclic organoborones. So we can cause formation of hydroboronation of dienes only by using texyl boron, as texyl boron can form cyclic or bicyclic organoborones. Now see, this is the example. This is the diene. On reacting with texyl boron, it forms a cyclic compound, cyclic organoborane. So this, what happens is, this is being donated and this is being donated. So two double bonds terminal alkenes carbons donate the pi electrons to form this kind of complex. Now we see that texyl boron can cause formation of trialkyl boron with 3 different alkyl groups. So this is a function. If we see, this is an alkene, cycloalkene, right? It is a 6-membered cyclohexene. So this on reaction with texyl boron forms this kind of hydroboronated compound. Now again, if we add a polar compound with a polar substituent present in it, and this is also an alkene, then we see that a boron is being formed with 3 different alkane groups, right? Now hydroboronation occurs in alkenes with many types of functional groups. So this is important, that it can support many kind of functional group, that is, these functional groups are not reduced by boron. Hydroboronation generally proceeds without difficulty, and even some functional groups can react, but it is slow. For example, Carboxylic esters react slowly. Now easily reduced carbonyl groups requires protection, like ketone, aldehydes, these requires protection during the hydroboronation. Okay, carbonyl groups can be protected as acetals or carboxylic acids as esters. Now see, this is an example where we have used another kind of borane to promote the reaction and get the usual regioselectivity. Halogenated boranes react with usual regioselectivity with the addition of boron atom to the less substituted end of the carbon-carbon double bond. But although they show this kind of behavior, but not always. Suppose if we take for dibromo borane, then it will react with to form the hydroboronated compound in this side where there is more substitution. Whereas if we take normal decimal borane, then the reaction takes place where there is less substitution. So we have to remember that in case of this one, the reaction takes place in the more substituted part, and for the normal case when we use the decimal borane, it takes place from the less substituted part, and this is the substitution portion, right? Now this was the end of the hydroboronation part. Now application of the hydroboronation part is very important and it will be discussed in the next video. So thank you for watching. Do not forget to like, share, subscribe and comment.